Hi, this is Dr. G Vikas Paul. In this session, we are going to discuss about beam column, which is also known as laterally loaded struts. So, a beam column is nothing but it is a structural member subjected to both axial load and lateral load. Generally, axial loads will be subjected on columns, lateral loads, beams. So here, any structural member, if it is subjected to both axial load, vertical load, and horizontal load, lateral load, then it is known as that structural member is known as that column is known as beam column. Okay, these members experience combined bending and compression. So due to these loads, it will experience both bending and compression, making their analysis more complex than pure beams or columns. So to analyze this type of beam columns, it is little bit complex than pure beams or columns. Examples of beam columns: columns in frames subjected to wind or seismic loads. This is a frame. So here the columns will be subjected to vertical load and horizontal forces. That is wind, horizontal means wind forces, or earthquake loads, seismic loads. And another example is vertical members of a multi-story building. Vertical members of multi-story building are also subjected to wind force, seismic force, and vertical forces and horizontal forces. So they are known as beam columns. These are the examples of beam columns. Real life examples: reinforced cement concrete or steel columns are resisting along with the seismic force or wind forces. Then compression struts in trusses with additional lateral loading. This is a truss, and so with additional lateral loading, what happens? These struts are subjected to both vertical and horizontal forces. Then portal frame legs under gravity and lateral loads. Portal frame legs under gravity and lateral loads. So these are the beam columns. Now, so what is the governing differential equation for a prismatic beam column, elastic, subjected to axial load P and lateral load W into X? So if you take a beam column here, it is subjected to axial load P and horizontal force W into X. Okay, so lateral load function W into X. Then the equation is EI d power 4 y by dx power 4 plus P into d square y by dx square equal to W into X, where EI is relative rigidity, Y is the lateral deflection. So due to this force, horizontal force, lateral deflection will be there. It will bend like this. So lateral deflection is this is your Y. Axial compressive force is P, and the W into X is lateral load function. So there are two cases here. One is uniform axial load P and lateral load W at midspan. If the total length is L at midspan, L by 2, L by 2. This is one case. Second case is vertical load P and UDL W over the entire length. Uniform axial load and uniform distributed load over the span. Okay. So for this first case, what is the first case? Beam column with axial load P and lateral point load at midspan. Okay, P and point load at midspan. For this case, the formula maximum lateral Euler's critical load formula is same: PE pi square EI by LE square. Okay, if we compare both these cases, this is the UDL case. Okay, so this is your Ymax. The formula to calculate this Ymax here is maximum lateral deflection is WL cube by 48 EI into 1 minus P by PE, where W is here, the formula is this one. Here the formula is 5WL per 4 by 384 EI 1 minus P by PE, where W is the load, lateral point load for this case, applied at midspan. Here W is UDL, and remaining are same, like P is axial compressive load, PE is Euler's buckling load, which we will calculate here using this formula. Remaining we know elastic modulus, length of column. So what is the maximum bending moment for this case? It is WL by 4. Maximum bending moment will be like this. Okay. WL by 4. So as this is UDL, it will be like this. WL square by 8. Maximum bending moment. if you observe here, it is like a simply supported beam. If you see, if you rotate this like this, if you see in this way, now it is like a simply supported beam subject to point load at center. For that, maximum deflection formula is WL cube by 48 EA. So here additionally this will come. In that way also we can remember. So for this, pi WL power 4 by 384 EA, and additionally this will come. In that way we can remember, and maximum bending moments are same. Okay, right. Okay. Thank you. Let us discuss problems. Here we have two problems. First problem is for first case. Axial load is given, horizontal force is given, length is given, everything is given. Just we need to find the maximum deflection Ymax at center. This one Ymax. So we know the formula. Substitute everything in this. But here PE we need to calculate. Pi square EI by LE square. So what is LE here? In question it is given both ends are pinned. So effective length equal to length, original length. So 3 square. You will get this PE, substitute here, you will get Ymax. So for second case, we need to calculate maximum deflection at a center. So here also we know the formula for Ymax. Before calculating Ymax, we need to calculate this PE here. Okay. Here also both ends are pinned, so L equal to L. Ymax maximum bending moment WL square by 8. Thank you.